And now for the Model Analysis Lab, where we'll put the materials for this week to work. For most of this lab, we're going to focus on a kind of a little toy model, which is described in the figure here, where there's an inflow that's constant to a stock that has a fairly large initial value relative to the flow, and its outflow is a function of what's in the stock divided by a small constant, so it's a large outflow relative to the size of the stock. The value of the stock then influences a flow into another stock that starts at 0, and the flow rate depends on the difference between A and B. You'll notice a slight similarity, perhaps, to the hand integration example with the two tanks, but it's different, and that means the analysis has to be nuanced somewhat. If you look at the loops, you can see that A influences A, or you could draw it the other way, but basically A is a self-loop there, and also B influences C, and then in turn influences itself. So the first loop is balancing with a kind of a goal of 0. It's trying to drain that stock. The negative link, the reason that that's balancing and not positive, is because when you go back after the blue arrow on the upper right, when you come back into the stock, you're going against the flow, which is a negative, as we talked about previously last week. The second loop is balancing, but the goal is not as clear. So there's clearly an inflow, and then there's a minus sign in the C equals A minus B, so we subtract the B values. That's clearly a negative or balancing loop. And if C decreases, then the flow decreases. And if the flow decreases, that means the effect on B is decreasing, so that's is the other way to look at that as a balancing loop. Well, did looking at these loops help you get a sense for how the system is going to behave? I found it to be not very satisfying. I think the second loop in particular is troublesome, and this is very often in models the case, because even though the flow into B decreases, if B decreases, then B itself does not decrease, since some amount is still flowing into it. So it's just a little bit murky seeming. So it's not a clear case of the notion that if B increases and the direct effect of the loop is then a feedback, a negative amount that subtracts it. So it's just a little bit more, it's muddier, I guess. Second, it's not clear how A fits in. What's exactly going on? It's not actually in the loop, but its value is clearly influential. So let's see if constructing a causal loop diagram, maybe it'd be a little bit more clear. Just for reference, in case it helps to draw the flow diagram from the equations, here's the equations. The rate of change of A is 5 minus itself, A over 2. C is the difference between the two variables, the two stocks. And the rate of change of B is just this difference, the variable C, divided by 2. There's a lot of symmetry and interesting stuff in this little toy problem. All right, so here's the CLD. Ignore the squares around the letters. A influences itself, and C is connected to B, and B is connected to C. I didn't put the signs on here, but you can clearly see that this doesn't really shed any new light. Studying the second loop a little more clearly on the flow diagram actually might be better. What's the goal of the loop? Since C is 0, when A and B are equal, B will stop changing when B equals A. Thus, the goal of the loop for the value of B is to be equal to A. What does this tell us about how B will behave? It tells us that the second loop drives B towards A, wherever A is going. Maybe that's a little bit more useful. So the key idea here is, to summarize, while tracing feedback loops and considering their polarity can be insightful, it can also be inconclusive. Sometimes we can reason out the behavior by a more direct inspection of the logic of the model, rather than relying only on looking at loops and loop polarity. Now, using the same example, we'll use the second part of the material for this week, model behavior without using hand integration. And we'll start by considering the basic shape of the trajectory. So looking at the model again, Are we thinking that we're going to see linear type behaviors, exponential behaviors, or what? So A has a linear input and an exponential output, meaning that the input is constant. It accumulates linearly. That's the meaning of linear input. And the output is proportional to the amount remaining. What does this imply? In order for the trajectory to be straight, I'm just reading here, but I'm not sure if I'll introduce some nuances as I do that. Both the inflow and outflow would have to be constant, and they're not. So that kind of right away tells us that A's trajectory should be curved. Since the inflow is steady and non-zero, A will not go clear to zero. When everything is stable, here's the thinking here, the outflow is still non-zero because the inflow is non-zero and it has to be equal at steady state. So it's kind of a dynamic equilibrium. For a non-zero outflow, A has to be non-zero. Therefore, since its flow is proportional to the value. Thus, we know that this system, this little part of the model, is going to be curvy and it's not going to go all the way to zero. Now, B is neither simple linear nor simple exponential because its rate depends on B and A through C. So it seems that B will curve upwards at first since it's empty and there's going to be a lot coming in initially. But then it's harder to know what's going to happen. And we'll study that's what some of the other approaches to model behavior are for, and we'll be testing those out with this example. So let's look at departure angle. We spent quite a bit of time in the chalk talk earlier on that. Is A headed upwards or downward as it leaves the axis? It starts at 100. What's its initial outflow? Well, it's 100 divided by 2, so there's a huge amount flowing out, much more than what's flowing in. So A is going to be heading down sharply at first. And what about B? How would you compute this? How does it leave the axis? So to compute B's initial flow, first we compute C, which is A minus B, which is 100. Then we compute the flow, which is C over 2, which is 50. So B starts upwards, just like B crashes down, or A crashes down. B is going to be zooming upwards because of that huge difference. All right, so we know they're zooming up and down, or down and up respectively, but are they curving? We know they're curvy, but are they curving upwards or downwards? So the trick here is to compute the net flow rate. Just imagine a little bit of time has elapsed and A has drained. It's not nearly a full time unit or anything, but A has now decreased to 80 and B has sort of increased to around 20. It won't be exactly that. It's a thought experiment. What would be happening then? So if the flow out of A had decreased at this point, then its outflow would be curving downward, but at a decreasing rate, since the flow rate a short time later is less. So when that's happened, if A is at 80, now the outflow is going to be 40 instead of 50. So it heads down really fast, but the rate at which it's heading downward starts to decrease. Carry out the same kind of analysis for B, and you discover that B is heading up very rapidly, but quite a way as these two variables approach each other, B's rate of change slows down quite rapidly. So it heads up rapidly, and then that ends up being what we described earlier as increasing at a decreasing rate. So now we're starting to get a picture of how these two variables' trajectories start out. Can we figure out anything by considering asymptotes? At what values will A and B approach? What values will they approach eventually? And when do their rates of change go to zero? We can do that with fairly simple algebra. When does the outflow of A equal its inflow? Since the outflow is A over 2, and if the inflow is 5, then at the value of A equals 10, divide that by 2 equals 5. So now the inflow and the outflow would be matched. So we know that the asymptote for A is 10. So now let's set A to this value, stop it right there and say, what would be going on with B at that point, and analyze B. At what point will its flow be 0? Its flow is C over 2, which equals 0 when C equals 0. Since C is 10 minus B, it's going to be 0 when B equals 10. It's kind of some symmetry designed into this example. So the asymptote for B is also 10. This is pretty useful. So now we know that over at the right-hand side of our little plot in our mind, both A and B are going to be heading towards 0. Excuse me, towards 10. Sorry for the busy slide, but it's all on the same subject. Are there going to be any turning points? These occur when the variable changes from increasing to decreasing in value, i.e. when its net flow is 0, but transitionally rather than as an asymptote. Consider A. It starts at 100 and it's exponentially approaching its value of 10. Will there be a turning point? No. It just keeps going down, it's curving, glide into the value of 10. We can draw that part of the curve right now. We can draw A's trajectory very confidently and pretty exactly without having done any full hand integration. We've just done a little bit of careful thought about what's going on. Consider B. It's starting at 0 and rapidly going up. When does its net flow go to 0? Well, when A and B are equal. Can this occur anywhere except perhaps at the long-term asymptotes? So this is another little thought experiment. Consider the initial rates of change of A and B. Of A, it's minus 45, it's heading down fast, and B is heading up fast, slightly faster actually at 50. If we just moved out one time unit, A would be down, and we didn't get it exact, we just did the Euler approximation like we did with hand integration. It would be down to about 55, while B would have shot up to almost 50, perhaps. So already the difference between them has dropped from 100 to about 5. If their trajectories were to cross, what would B's flow rate be at that point? Well, it would be 0. So, and that's only going to take a little bit past one time unit. Maybe it's 2 time units, given that we've made an approximation. Its rate will be 0. The time is kind of a guess. We don't know it exactly. But that's not the point. We do know that B will be flat at that point. So when B curves over and crosses the value of A, B will be horizontal. Its trajectory will be horizontal at that point. Just after that, B is now larger than A, so B's flow rate becomes negative. So this would be a turning point for B from increasing in value to decreasing in value. Now B's trajectory will be very slowly decreasing and chasing A towards 10. So what about inflection points? These are more subtle, sort of higher order effects where the curvature of the trajectory changes from curving in one direction to curving in the other direction, i.e. going from, say, increasing at an increasing rate to increasing but at a decreasing rate. Does A have any inflection points? What about B? Well, A does not. It remains decreasing at a decreasing rate all the way to its asymptote. B, however, as we've already started to realize, has one. We haven't seen it quite yet. It occurs a little bit after the turning point. Right at the turning point, B has just begun to decrease, so it's decreasing really slowly. But now it's trying to catch up and chase A, so it starts going faster and faster. But then as it gets close to A, it has to slow back down again. So there's going to be a place, and what I like to imagine here is that if I had a couple of coins, or just take a round circle, like a piece of round paper or a big coin, and I say, well, which side of the curve does the coin fit on? And if I get to a point where I have to move the coin to the other side of the trace, then I've had an inflection point. So this is not as critical for you to be familiar with, but this example nicely illustrates a place where there's an inflection point, where it's curving on, your coin's on one side of the curve, and then pretty soon you have to move the coin to the other side of the curve as it glides in to touch its inflection point, sort of chasing after A in that process. And just for completeness, let's consider the other aspects that we mentioned in the chalk talk. Is conservation of mass useful here? Well, no, because there are 2 storage that are not coupled, so the outflows and inflows don't have to match. There's really no total that we need, that we know it has to equal over time. We are sort of using conservation of mass when we figure out the asymptotes, because at that point the amount flowing in and the amount flowing out are equal. But it doesn't, other than that, it doesn't really help us. Is there any sort of an envelope? Well, not really, because the inflows and outflows are not constrained to achieve any particular values. We did, however, see examples of envelopes, I don't know if we described them that way, in the hand integration lab, because the tanks were coupled, and the total of the 2, if you were to look at it, and we talked briefly about that, it increases at the rate at which water is entering the tank, since in some of those examples there was no outflow. That's all I want to say about the lab, and I'll just close with a comment that if you've gotten to this point and you're pretty comfortable and you feel sort of caught up, that's wonderful, and I would encourage you to take a look at some of the choices for exercise 2 and start thinking about that.